Okay, so the plan for today is to discuss volumes by finding volumes by the shell method or the cylindrical shell method. I think that's going to pretty much take the lecture time today. And then again, remember this being a hybrid course, we have 40% of the material, or a little over an hour of the kind of lecture time, is replaced by something like supplemental videos or supplemental work. So what I'll do in the next day or two, I'll have a supplemental video posted to YouTube, and that'll be kind of a just like a class supplement. You can work through that video, watch it at your convenience, and then there will be the 6.1 through 6.3 homework also to work on to kind of firm up those concepts. So typically what I'll do is I'll try to do an introduction to a given section in our actual class lectures, and if you have questions you can ask them then. And then typically I'll leave to the supplemental video maybe some of the maybe like a more challenging problem, or a problem that's maybe a little more offbeat, or kind of a tangential idea related to the idea that we covered. So typically that's going to be kind of the structure, not necessarily saying it's always going to be like that, but that's going to be my usual strategy for what to put in the lecture versus the supplement. And then one thing that I mentioned here is I posted the YouTube playlist, which is where I'll be posting the class meetings there as well as the supplemental videos. Let me show you where that is. So if you go into the Blackboard site under useful websites, you'll see this new line here. And the YouTube videos can be found here, and that's a hyperlink. So you can click on the here, that'll bump you over to the YouTube playlist for Calc 2. Yours might look a little different than mine, but it'll look like this kind of a playlist. Sorry. And you can see that I have class meetings 1 and 2 posted. So I have the Zoom links up for those, but sometimes YouTube can just be a little easier to access. It can, work a little bit better on, say, a phone, or you can get it on your TV, that kind of thing. Where Zoom's a little more restrictive. And also this way, the other benefit of doing it this way, I've just started doing this really this semester. The other benefit is Zoom deletes the recordings after, I think it's 120 days. So even if you have the Zoom links for the recordings saved, if you go into Calc 3 and you want to go back and review something, chances are the material you want to review will have been deleted by Zoom by that point. But these YouTube links, they'll stay up there pretty much in perpetuity. So if you take Calc 3 over the summer or the fall or something, you can always refer back to this material, and I'll just leave these links up indefinitely, these videos. Okay, let me switch back. The quote of the day today, really kind of a quick idea. This is from chess grandmaster Daniel Naroditsky. He does streaming and YouTube videos and things. Very entertaining and informative to watch if you're at kind of the advanced beginner or early intermediate level, which is probably a bit of a stretch for me, but he has a lot of good content. And one of the things that he likes to point out is that there's a difference between abstract and concrete advantages. So kind of related to chess, that might mean you have a lead in development. You have 3 pieces out while your opponent only has 1 piece out, but that advantage can disappear pretty quickly. Whereas if you, say, capture an opponent's piece, the opponent is without that piece the rest of the game, you've converted that to a concrete advantage. So a couple examples of this may be something like getting a degree in a field versus working your way toward a career position in that field. If you want to, be an engineer, getting a degree is a nice step. It's an advantage to getting in that field, but it's more abstract. It kind of, opens up the possibility of becoming an engineer. And you really have to do a couple other things to bring that home. Another example is is something like knowing about a thing versus doing the thing. So this might be knowing which exercises are good to increase fitness or strength or whatever versus actually going to the gym, or learning about a language, learning what kind of structures it has, learning about the people versus actually practicing speaking the language. Or in math, this might look something like, attending lectures and kind of understanding in a general way, in an abstract way, say what the shell method is, versus actually going in and, going to the book, picking a couple of problems, working through the problems, really drilling that, going to the homework, completing the homework questions, and really drilling the idea of, finding volumes using the shell method or using the disk method or whatever. So that kind of, abstract understanding has to be really solidified into something a little bit more concrete. And things like the homework or rewriting notes, or the class activities out, or the class work that are outside of the lecture, is really important for converting that abstract advantage into something more concrete. Okay. So now getting into the main part of the lecture. So finding volumes using the shell method. We talked last time about finding volumes using the disk or the washer method. But what about this shell method? Well, let's consider a solid obtained by rotating a certain region about the y-axis. About the y-axis. So here we're going from x equals 0 to x equals root pi. And my region is this y equals sine of x squared. So sine of 0 squared is 0. And if I put in root pi, I get root pi squared is pi, sine of pi is 0. And we're basically inputting into sine the numbers from 0 to pi. So we know that we're positive on this interval, and maybe the curve looks something like this. Not going to quite look like sine x on 0 to pi. It's going to be a little deformed. And then we're rotating this about the y-axis. So this is my region R that I'm rotating about the y-axis. What does my solid look like? So I have something like this over here. Let me redraw that a little nicer. And then I have the mirror image on the other side. I'm rotating it around kind of horizontally, so to speak. Oh, OneNote loves to try to help out a little too much. There we go. And so my solid looks kind of like this. It looks like if you've ever seen like a bundt cake pan, or like if you cut a donut in half sideways, that's kind of what it looks like. It has like this kind of circular kind of hump with like a hole in the middle. Maybe not quite a complete hole, but something, like a divot in the middle. Now I might say, okay, well, I have a way to find a solid. I see that I have this nice rotational symmetry about the y-axis. Maybe I'll consider the plane PY perpendicular to y. That'll give me a cross-sectional area, and then I can integrate over that cross-sectional area. Maybe this will be a good approach. I see when I slice through this solid, I'm going to have an outer radius and an inner radius. So I'm going to have an annulus, like the area that's inside of a bigger circle, but not inside of a smaller circle. So this is my area for a given height y, a given position on the y-axis where my plane is cutting through. And I see that I have two radii. I'll call them R1 and R2. So I might say this is like pi times R2 squared, pi times the bigger radius squared. That gives me the area inside the bigger circle minus pi R1 squared. So taking away the area that's inside the smaller circle. Okay, this isn't too bad. I just need to find these radii. So for a given y, I need to find the two values of x associated with it. In other words, this is R1, this is R2, and these are the x values associated with a given value of y. And I see something kind of unfortunate here. I see if I have y equals sine of x squared, I need to invert this to get x in terms of y, to say for a given y, what is my x value? Right, I want these radii to be in terms of y so that I can integrate from y equals 0 to y equals 1 of this thing. Number one, this just isn't going to be very nice to invert. I'm going to have kind of a plus or minus square root deal going on here. It's going to be kind of annoying algebraically, but probably the bigger problem is that I need to plug into here and then integrate. I'm going to have a very messy function to integrate. So while my washer method, my disk method, it works nicely for some problems. It works very nicely for some problems. It maybe isn't the best method for all problems. So let's see if we can take a different approach. I'll copy most of this work down. Maybe I can't copy as much as I was hoping. I guess I'll just copy the region picture. I'll redraw the solid. Again, it does take a few minutes to draw these pictures, but I think it is really beneficial to draw them, just to really keep in mind exactly what's happening. So again, I have my kind of, bundt cake or top half of a donut kind of deal. And let me actually zoom this in a little bit, make it a little bigger. So here I would like to come up with a different way, a fundamentally different approach to finding the volume here. Now I want this different approach. This should give me the same volume that I would theoretically get if I used the Disker washer method. I want to account for all the volume in the same way. But I want it to be different in the sense that that I can apply it to problems that don't work great for the Disker washer method, that it's kind of a complementary method. So the Disker washer method, kind of what it fundamentally does is it starts at one side, maybe top or bottom or left or right, and kind of adds slices going all the way to the other side. So it starts at left and goes all the way to right, or starts at bottom, goes all the way to top. But we see that a lot of times we're dealing with solids that are solids of kind of rotation. There's a nice rotational symmetry to these solids. Sometimes that nice rotational symmetry translates into a nice symmetry over in the cross-sectional area, and that could definitely be helpful. Can we develop an approach, a method of finding the volume of the solid, that kind of starts with that nice rotational symmetry? Now, this approach is probably going to be a little less generalizable than the Disker washer method, because if we start with that symmetry, we're really leaning kind of heavily on it. But for problems that have this symmetry, maybe exploiting that symmetry from the outset will be really helpful. And that's something that there's a saying, I think it might be from a physicist, or I forget who said it, but they said something like, when there's symmetry in a problem, you're almost always rewarded for exploiting it or for recognizing it. So that's something that, that we're going to see throughout this course and really throughout mathematics, is when there's an inherent symmetry in the problem, if we can really lean on that symmetry, a lot of times that makes things quite a bit easier. So the idea here is there's a rotational symmetry. So I can think of adding slices, in a sense, instead of left to right or top to bottom or bottom to top, which kind of really doesn't respect that rotational symmetry inherently. I could think of adding slices radially, from inside to outside, or from near the axis of rotation to further away from the axis of rotation. In other words, instead of using a plane with a cross-sectional area, I can imagine constructing a cylinder or a cylindrical shell, say starting on the very inside and progressing to the outside. Now, when I was thinking of that planes and cross-sectional areas and things, I really thought of having kind of a fill-it-in cylinder of, let's say, height or maybe thickness, delta x, a certain small thickness, lining them up next to one another, all of these different size cylinders, creating kind of an approximation to my solid, and then kind of taking a limit. I'd like to do the same kind of thing here. I would like to really think of this cylindrical shell as being a cylindrical shell of a certain thickness. I'm going to try to draw this fairly carefully. I know it takes a little while to draw these things in a way that looks pretty nice, but I think it is really helpful. Well, my walls should be nice and straight up and down, but they don't look so straight, but they should be straight up and down. I want to take a shell of thickness, let's call it delta x. For a given x value, for this, say, value of x on the x-axis, I see that I have an associated height of the shell, y equals f of x. So this height here is going to be approximately f of x across the whole shell. Now, whether I use kind of the inside of the shell or the outside of the shell to get my kind of bearings on the measurement of the height, it'll change a little bit. But again, if delta x is quite small, and if f is a nice, continuous function and so on, then the discrepancy between whether I measure the height at the inside or the outside of this shell really shouldn't matter. And then when I take the limit as delta x goes to 0, of course, any of those problems go away in the limit. And then the last thing I need is I need a third dimension. And the third dimension is the kind of radial distance of the shell. Again, whether I go to the inside or the outside edge, whether it's x or x plus delta x shouldn't matter because delta x is going to 0. So we'll say this is approximately x. What's the volume of such a shell? I can imagine I have this kind of cylinder. I can think of like taking scissors and cutting one side of it and laying it out flat. When I do that, I end up with something that's kind of like a cuboid like this, like a box. And again, if I laid it out flat, maybe the side that came from the inner radius would kind of pull in a little bit. Maybe it would make more of like a trapezoidal type shape. But again, since we're only talking about delta x difference and delta x is small and going to 0, that's something that we can really not worry about too much here. So this is my box. Again, I kind of am thinking of slicing down, say, one side of this, and then peeling it out and laying it flat. So this box will have like front to back depth, delta x. It'll have height, f of x. And it will have width. Well, x is the radius. So the width of this box is going to look like the circumference around my shell. So if I had a little, like soldier or something marching on top of it and they made one lap all the way around, what would that distance be? That would be, so that's 2 pi times the radius, or that's 2 pi x. So I can see this little contribution to the volume. Maybe I can say that this is like the ith shell, and maybe this would be like x sub I. So I'd have like, the first shell would be the very innermost one that goes from x equals 0 to x equals delta x. And then I'd have a second shell that would kind of wrap around that one, and a third shell that would wrap around that one until I build them up and I'm all the way out at x equals root pi. So what's the volume of this ith shell? We'll call it VI. And it's going to be approximately 2 pi x, f of x, delta x. Now, just as kind of like a, I don't know, an intuitive, intuitive analogy for this. I don't know if this is still something that they do, but when I was a kid, like, all of there like wasn't as much safety and stuff as there is today. And my sister and my parents would take us to some of these like these fairs where it's like, Revolutionary War reenactment or something, or like where you see them, making textiles on a loom and, some of those kind of things. And one of the things they would do is like candle making. So you take a bare string and they'd have some melted wax and you like lower the string in, and there'd be a line of kids doing this. You lower the string in and it makes a coating of wax. It's very thin on that string. You go to the back of the line, and by the time you're up to the front of the line, that has dried, and you dip it in again and it makes another coating around. And you do that a whole bunch of times and it builds up, and then you have a candle. Or what they would actually do is you would do it with your hand. You could like put your hand in and hold your hand really still, and then you go to the back and you put your hand in again. And I don't know what kind of wax it was. It like didn't really burn you or anything, but you do that a whole bunch of times, and then you can like cut around the edges of your hand and you have like a form of your hand that's been built up. So this is what I kind of think of when I think of this. So building it an innermost layer and then wrapping the next layer around that, the next layer around that, and so on until we get the full solid build up, at least approximately, right? It'll have kind of these like jagged edges going along here for the approximation. But when we take the limit as n goes to infinity, as delta x goes to 0, the number of shells goes to infinity, the thickness of the shells goes to 0. We'll pass from a sum into an integral, and that everything will smooth out nicely. So what's my overall volume then? It's approximately sum from I equals 1 to n of 2 pi xi f of xi delta x, where delta x is just b minus a, or root pi minus 0 over n. This should look a lot like it should have a feeling of a Riemann sum. We say our volume equals, then we take the limit as n goes to infinity, which takes delta x to 0, because delta x is b minus a over n. B and a are fixed. N going to infinity drags that to 0. Our volume then is integral a to b 2 pi x f of x, and then delta x becomes the infinitesimal dx. And we see that that is our formula down here, derived pretty much from first principles. This is the idea of the shell method. And again, even when this formula applies, I like to draw out the region, what axis we're going around, draw out the picture, and maybe even draw out a sample cylindrical shell, just to make sure I've got everything right? If I was rotating about the x-axis instead, my variables might look a little bit different in here. Or if I was rotating about an axis, rotating the same region about, say, the axis root pi instead, I'd have a different solid. My formula wouldn't directly apply, but I could look at how I could take the same idea and adapt my formula to apply it to something more general. There's an idea that I like to think about, and I might say this a couple of times during the course, but this is just a very abstract idea. So if you think that like this axis represents like the space of problems you might come up on and try to solve, and that problems that are nearer to one another on the axis are a little more similar to one another. If you have a formula that you just it's just like a tool in your toolbox, and you apply it, and if you see this problem, you apply this kind of formula, end of story, then your ability to solve problems kind of looks like this. So problems that fit really nicely into this mold, you can solve them super well. But even if I take this very similar problem and say rotate about an axis x equals root pi instead, well, your formula doesn't work. You're kind of at 0 ability to solve the problem. If you understand the background, if you understand things a bit more fundamentally, if you understand where it comes from and how we got this formula, you don't have to go through this whole calculation every time. But if you understand this, then your ability to solve problems looks a little more like this. Right? If there's a problem that's pretty near the types of problems the formula directly applies to, if you understand the strategy, the idea behind where the formula came from, you might be able to do a good job of adapting that idea and come up with an approach that probably gets you pretty far. It gets you pretty close to a solution. And of course, still the further away you get from your kind of canonical problem, the less helpful that is. But you get an awful lot more area under the curve, in a sense, by understanding the fundamental idea than by just knowing here's the formula and here's when I apply it. So that's why we go through this background. That's why we do things like, proofs and things like that. It's really to show you where these ideas come from, and then you can generalize those ideas when needed in the future to, attack similar looking but slightly different problems. Okay, so if we wanted to bring this one home, there we go. So my volume then is going to be the integral from a to b. Am I going to integrate from negative root pi to positive root pi? Well, no, because remember, our variable of interest is this x, this radial distance. I'm starting building up my shells at the inside and going to the outside. So I'm really starting at my axis of symmetry at 0 and adding shells going this direction. And when I add a shell a little further out, it kind of wraps around and takes care of the left side. So it's important, again, to understand where this comes from. What a and b should I choose? It's not negative root pi to positive root pi. I start adding shells at 0 and continue adding them out to root pi. 2 pi x, f of x, my height, is sine x squared dx. And with a pretty straightforward substitution, we could solve this. So if you want a little bit of practice, go through and figure out the numerical answer for this. All right, so a few examples. Are there any questions so far, by the way? I do have chat open over here, or if you have questions, you can always just kind of speak up. I do have my meeting controls hidden, so if you do something like, raise your hand or something, I think that is hidden, but you can pop something in the chat or speak up if you have a question. Okay, so example, compute the volume of the solid by rotating this region R about the y-axis. So we are going about the y-axis, and R is the region bounded by these curves. So y equals 4x minus x squared, or that's x times 4 minus x. This is going to have roots at x equals 0 and x equals 4. And we see that it's opening down, so it's going to have a vertex up here at 2 comma something positive. We have another curve, y equals x. So this is our region. And again, we're rotating about the y-axis, so we're rotating this direction. We're going to see a little bit of a nuance come up here. We're going to, I think, have to revisit our formula and our initial setup for developing that formula. I'm going to try to stick with my color scheme here. And I actually don't want to write 4 down right now. I'm going to figure out what that number is in a minute. This is where I'm going to stop adding shells. I'm rotating about the y-axis, so I want a mirror image on the left. Then I have this kind of outer piece on the top. And so this looks a little bit like kind of a funky ice cream cone something like that. And again, if I imagine a shell, so I have a shell here at radius x, it's going to wrap around. I'm going to have a shell piece over here. That one's supposed to be dotted. I think OneNote filled it in. But something that I noticed now is I still have thickness delta x. I still have radius x, but my heights are a little different, right? My height isn't just like 4x minus x squared. My height is actually the difference between the blue and the green curve. I note that the blue curve is always the curve that's on top, that's associated with the higher y value, and the green curve is always on the bottom. So the height of my cylindrical shell is going to be blue function minus green function. Or this height is going to be 4x minus x squared, subtract my green function y equals x. So here I have like an f of x needs to be replaced with like f of x minus g of x. So in fact, right, my construction up here really leaned heavily on this bottom boundary being y equals 0. But if I want to generalize a little bit, right, up here I had the special case g equals 0, but more generally, my height is going to be top function minus bottom function. If I have a bottom function that's not just the x-axis, or if it was rotating around the x-axis, that wouldn't be just the y-axis. So really understanding where this comes from, again, lets me adapt this instead of me just saying, oh, well, what do I pick for f? I have two candidate functions. I'm not really sure. I really understand, okay, the f is what relates to the height, and the height ought to be the difference between these two functions. That's what's sensible looking at the pictures, right? If I didn't have these pictures to look at, I think it would be a lot more difficult to interpret what's going on here. And this is, of course, just going to be 3x minus x squared for the height. Okay, so what's my volume going to be? It's going to be integral of 2 pi x. That came from 2 pi times the radius is the circumference, approximately, times f of x times the height of each of the given shell. 2 pi x, f of x, or more generally, f of x minus g of x, dx, my thickness becomes the infinitesimal dx. I start adding shells at 0 and continue adding shells until somewhere. So we're starting at 0. And how do I figure out what this is? Well, I set the two equal to one another. 4x minus x squared equals x. 3x minus x squared is 0. Or just when this height here reaches 0, when the height of the shells reaches 0, that's when we've added the last bit of shell that we need to add. Or this is x times 3 minus x is 0. So clearly x equals 0 or 3. So we start adding shells at x equals 0. We continue adding shells until we get out to 3. Again, we don't integrate from -3 to 3. We're adding radially, starting with the axis of symmetry, the axis of rotational symmetry, the y-axis, or x equals 0. And we continue adding radially. When we add radially, wrapping around takes care of the left side until we get out to our last shell out here at x equals 3. And of course, this is just a polynomial. I'll leave it as an exercise to carry out the integration and get the numerical solution. But really with these problems, the crux of the problem is setting up the integral and really drawing the pictures and getting all of the pieces sorted out to make sure that the integral we set up is actually representing the volume, right? I could very easily have just looked at this integral here and just grab this function or something, and I would have set up the wrong integral. So again, these pictures take a little while to draw, but I think that's really a very important part of the problem. The other benefit of these is starting to kind of get used to drawing things in 3D or interpreting things in 3D is super helpful for Calc 3. It's a very good skill to have in Calc 3 when you're setting up multiple integrals and things. Just figuring out the regions of integration and all that, super helpful to be able to, at least at a rudimentary level, you can see I'm not an artist, but be able to get an idea of what's going on in 3 dimensions and be able to write something or write a picture down that at least is a decent enough approximation of what's going on. Any questions on this problem? Okay, so the next one, similar idea. A little bit of a difference here. We're rotating this region about the line x equals 2. So not about one of the axes. Okay, so let's look at our region. So we have x equals 0 as one of the boundaries, the y-axis. We have y equals 1 as one of the boundaries, this horizontal line, and y equals x to the 4th, which goes from 0, 0 to 1, 1, something like this. So this is my region. And I'm not rotating about the y-axis or the x-axis. I'm rotating about the axis x equals 2. If I was rotating about the y-axis, I'd have something that would look like a kind of a filled-in bowl. If I was rotating about the x-axis, I'd have something that would look like kind of a little bit like a donut shape or a bundt cake pan shape, or maybe like a, football stadium or something like that tilted on its side. But here I'm rotating about the axis x equals 2. I haven't encountered something like this before, but let's see if I draw the picture, can I take the same strategy? I probably won't be able to use exactly the same formula as before, but can I take that same strategy, build up cylindrical shells, and figure out kind of from first principles what integral I got to set up and solve? I want this to be 2, the axis of rotation. This will be 0, and this will be 4. Okay, so I see going from 0 to 1 on the left-hand side is where my region is going to be living. And again, I'll try to stick with consistent colors. So at x equals 0, I have my vertical boundary. At height y equals 1, I have my horizontal boundary. And I have this curve going from 0, 0 to 1, 1. So my blue curve, y equals x to the fourth. My green line, y equals 1. I'm going to mirror image that on the right side. I'm rotating about x equals 2. This vertical red line is 2 units to the left of the axis of rotation. When I rotate around, it's going to turn into a vertical line at x equals 4, 2 units to the right of the axis of rotation. You might be able to, when you get used to doing this, not have to draw the whole solid out. I still like to draw the whole solid out because I think it really just really helps me visualize exactly what's going on. So I have my curve that's going something like this, and my top piece here in green. And I have this kind of inner top radius. I have an outer top radius. I have a bottom radius as well. So to me, this almost looks like if you imagine a filled in cylinder, and then you took one of those nuclear power plant like smokestacks that have that curving in shape. It's almost like if you took a cylinder and cut the smokestack shape out of the middle. So the volume is like this bit here and this bit here, but not these pieces. I think that's really important because that's going to change where we start and end our shells, or well, it's going to change where we start our shells. And it also, of course, changes the upper and lower functions and all that. So what does a shell look like? Maybe I'll switch to black for the shells. A shell might look like this. I'm being a little less careful about drawing my shells and making them kind of pretty, but this is more just an illustration now. So again, I see I have my shell. Thickness delta x. It's going to have a certain radius here. I'm just going to call it r. The radius is not going to be x, right? Because the radius is, for this x, it's this radial distance. So the radius, what's it going to be for a given shell at position x? The radius is going to be x minus 2. I'm going to build my shells going to the right. So your x is going to be from 3 to 4. And my radius is going to be x minus 2. I'm going to start building my shells here. This is the innermost bit of solid, working my way from the axis of rotation, x equals 2 outwards, and focusing on the right side. I'm going to start adding shells at x equals 3. Again, that x equals 3 shell will wrap around and take care of the x equals 1 bit on the left side. I'm going to continue adding shells with larger and larger radius until I get out to x equals 4, which will be a radius. So the radius will go from 1 to 2, but the x coordinate is going to go from 3 to 4. And what's the height of a given shell? Well, it's going to be green function minus blue function, or its height is going to be 1 minus x to the 4th. Again, Could I have done all of this just with that one basic formula up here? Well, no, I couldn't have. Could I come up with like a half a dozen different formulas, like one for this case, one for this case, one for this case, and then different formulas for if I was going around the x-axis kind of rotating around the x-axis direction instead of y. I guess I could have like, 6 or 8 or 10 or something formulas for all these special cases. But if I understand fundamentally this one formula from this simple case, again, that allows me to approach a much broader range of problems with this same solution strategy. If I understand the background well, I can adapt to a much wider range of problems. And I think that's one of the really important ideas throughout math is understand the fundamental structure, keep digging down until you get to something that's very foundational and very generalizable. That lets you approach a much wider range of problems with a similar strategy. Okay, so what is my integral going to be then? I start adding shells at x equals 3. I don't start at x equals 2 because that middle kind of cylinder from 1 to 3 is just empty. There are no shells there, or there's no solid there. There's no shells that I'm adding there. So I start adding at x equals 3, the innermost bit of the solid. I continue adding until x equals 4. Note that this is in terms of the variable x, not in terms of the variable r. The radius goes from 1 unit to 2 units, but the x coordinate goes from x equals 3 to x equals 4. We're integrating with respect to x because that's how our height functions for the shell are defined. We're integrating 2 pi times the radius, right? What's my little increment of volume here? 2 pi radius. That's my circumference times height times thickness. So this 2 pi radius, that's the circumference around the cylindrical shell, times the height of the cylindrical shell, times the thickness, delta x, which as we pass into the integral, we limit as n goes to infinity, as number of shells goes to infinity, the thickness goes to dx, goes from delta x to dx, thickness approaches 0. And again, how would we actually bring this home and compute this integral? Well, we just have constant times polynomial, multiply out the two polynomials, get a longer polynomial, integrate term by term, evaluate at x equals 4 and x equals 3, subtract them. That should all be pretty standard at this point. So the goal in this section is not to come up with difficult integrals and compute them. The goal is to understand how to build up from a fundamental idea, how to build up this these more general concepts that can be applied to different types of problems that are still in the same sphere, but a little different. And also that there's this idea that we've been using, whether it's in cylindrical shells or whether it's in the disk or washer method, the idea that we have a continuous problem, a nice continuous function, we kind of like discretize it. We split it up into chunks of discrete units, delta x. We get an approximate solution in that discrete setting. I use 100 washers or 100 disks or 100 shells. That gives me an approximate solution. It gives me a volume that's approximately the volume of the solid because it's based on a kind of a solid that's approximately the shape of the solid. And when I get that answer, I limit to get back to the continuous side of things. So I kind of start at continuous. I pass to this discrete. I start with dx kind of ideas. I pass to delta x. I get an approximate solution, right? I get an approximate volume, typically represented as a sum. And then I take the limit and goes to infinity, get back to the continuous solution. This general strategy, again, if we dig one layer even deeper, this idea of starting with a continuous problem or question, passing to a discrete version, solving it in a discrete version, and then passing back to the continuous side of things with a limit, we'll see this strategy over and over in even different applications throughout Calc 2. So things like finding, the average value of a function, or finding the work done in moving such a thing from here to here. We'll do a very similar process. We'll have a continuous question, we'll discretize it, solve it in the discrete world, take a limit to move it back to the continuous world. So we'll see this even more fundamental strategy over and over several times in Calc 2. Are there any questions on anything we've talked about today? Okay, so again, keep an eye out for that supplemental video in the next day or two. Review that, work on the homework, practice these problems, take this, maybe in a sense, this abstract understanding. You're like, okay, I've seen this before, I have a general idea. Move it into the concrete by drilling some problems and by doing the homework problems. And as always, if you have questions, I have office hours, or you can always reach out by email.